Hello and welcome to this video going through one of the high demand electric circuits questions. We're looking at question 12, which is the last in the pack of questions provided. So figure 1 shows the apparatus used to obtain the data needed to calculate the resistance of a thermistor at different temperatures. Okay, so we've got here a power supply, we've got an ammeter, current comes around here, we've got a voltmeter then connected in parallel, checking this side of our thermistor with this side, so see what the energy for each coulomb is here compared to the energy of each coulomb here. We've then got the thermistor inside a water bath, which has been heated by a Bunsen burner, and a thermometer over here. Okay, so I'm happy that I sort of understand what's been shown there. In the box below, draw the circuit symbol for a thermistor. Well, thermistor, it's a type of resistor, which all resistors have a rectangle, and this therm part here, if you remember your heating curves, if I take a solid and I heat it up, it does this shape, it follows this shape here. That's solid, that's the liquid, that's the gas. This bit here is where it's melting, so we've got solid and liquid. Here we've got liquid and gas, and hopefully what you'll notice is this funny hockey shape symbol there. That means that's to do with temperature, so when we get that hockey shape, that's it there. So that's our thermistor. So it's a resistor. I should write it in here, shouldn't I? It's a thermistor with that hockey stick going through it. And it doesn't matter which way the hockey stick's going, as long as it goes through it. Use data given in figure 1 to calculate the resistance of the thermistor at 20 degrees C. Okay, so I've got to calculate resistance of the thermistor at 20 degrees C. I have to use data given in, so use, that's also a command word. If I don't use the data in figure 1, then I'm not going to get credit for this question. So let's see what I've got. If I'm looking at resistance, I'm almost definitely going to have to use V equals IR. I know that temperature, which is capital T, is equal to 20 degrees C. What else do I know from this? I know that so in the diagram it's at 20 degrees C right now, which is great. So it's basically saying what's the resistance of this right now. Well, it gives me a current which is 0.025 amps, and it gives me a potential difference which is 9.0 volts. So I'm going to plug those both in. So 9.0 equals 0.025 times R. And I put the values in before I rearrange. R is equal to 9 divided by that, so 9 divided by 0.025 equals, R is equal to 360. So 360 ohms. Figure 2 shows the axes for a sketch graph. Okay, so sketch means no numbers. You don't have to put numbers or a scale for a sketch graph. Complete figure 2 to show how the resistance of the thermistor will change as temperature of the thermistor increases from 20 to 100 degrees C. Okay, so what it's asking for here is what's going to happen to resistance as it gets hotter. Well, for most devices, as resistance increases, as temperature increases, resistance increases. So most devices will have a positive correlation, have something like that. Now it might be a curve going up, it might be a curve going that way, or that. It doesn't really matter. The main thing is for most devices, as temperature increases, resistance increases. Thermistors are different. Okay, thermistors do the opposite. And it doesn't matter which way you have your curve, so long as it's a negative correlation. Okay? So don't worry if it's a straight line. It doesn't, we don't know. So long as it's a negative gradient, that's fine. Okay, next question. Which of the following is most likely to include a thermistor? So thermistor, heat dependent resistor. Tick one box. An automatic circuit to switch a plant watering system on and off. Okay, not sure about that. An automatic circuit to switch an outside light on and off. Okay, well, that's to do with light. Nothing to do with heat. So we're talking here about something to do with heat. An automatic circuit to switch a heating system on and off. Absolutely. The ammeter used in the circuit has a very low resistance. Why is it important that ammeters have a very low resistance? Well, ammeters measure current. So if you're measuring current, you don't really want to affect current, do you? You don't want it to change the current. There's no point at all. If you're measuring the speed of a runner, what you don't want is someone that runs out and stops the runner and gets in their way. You actually want to be as impartial as possible. You want to be as low resistance as possible. So why is it important that ammeters have low resistance? So they do not affect the current they are measuring. And the better the ammeter, the lower the resistance it has. The table below gives the temperature of boiling water using 3 different temperature scales. Okay, so 3 different temperature scales. We use Celsius or degrees centigrade here. So this is the temperature of boiling water. It's interesting. Scientists in different countries use the same temperature scale to measure temperature. Okay, so scientists in different countries use the same scale to measure temperature. Suggest one advantage of using the same scale. Well, the main thing there, I suppose, if you're showing the same scale, if everybody agrees to use this, which is pretty much what has happened, we don't tend to use Fahrenheit very often anymore. I'm not even sure, I've never seen that one before actually. But if everybody speaks the same language and uses the same data, then it's far easier to share results. To share results or compare results. Now, I only need to actually write one thing. Okay, but that's the main reason. That's what scientists do. They share results so they can compare their results. That's called peer review. So we do that process a lot, and it helps to identify errors and check. Part D, last part. A student plans to investigate how the resistance of a light-dependent resistor, an LDR, changes with light intensity. The student starts with the apparatus shown in figure 2 but makes 3 changes to the apparatus. One of the changes the student makes is to replace the thermistor with an LDR. Describe what other changes the student should make to the apparatus. And this is worth 2 marks. So 1, 2. Okay, so let's have a look at that apparatus again. So now they're going to change this. So rather than looking at a thermistor, they're going to look at an LDR, which is a light dependent resistor. So it's a resistor, it's got a window around it, and now it's light. So what do we want to do? Well, we want to change light. That will now be our independent variable, and the thing we're going to measure will be the resistance. But change light dark, well, the meter, that's a thermometer, heat meter. We're changing the heat doing that. We need to record light levels. There's no point having a thermometer. So we swap the thermometer for a light meter, and we swap the Bunsen burner for some sort of light, something we can do to change the light. So let's see how we can change that. So we change the change Bunsen burner. So we swap Bunsen burner and water bath for a variable brightness lamp, easiest thing, and we then swap thermometer for light meter. This word meter just means measurer. So an ammeter, I suppose should be really an amp meter, measures amps. An ammeter. A voltmeter measures volts. Always makes me chuckle here that a meter rule really should be called a meter, but that starts to get a bit crazy. Starts to get very confusing rather. So a meter. So if you're not sure what the thing is you want to measure, what the device is called, just use the word meter. So a resistance meter would probably be acceptable. We tend to call it an ohm meter. We sort of often put the units first. Okay, but if you're not sure what the device is called, then it's normally the quantity or unit, and then the word meter afterwards. Okay, hope that helps. Take care. Speak soon.